Okay, so today's speaker is Sthitadhi Roy from Oxford. So Sthitadhi studied at IIT Kanpur, then he went to the Max Planck Institute because in Dresden, and now he's in Oxford. And he's going to talk to us about, well, you see what he's going to talk to us about. I mean, one thing that he did mention earlier is that he feels more comfortable, and I also agree with that, when people have their cameras on. So, you know, I mean, if you don't mind, if you leave your cameras on, that makes it a bit more natural. All right, so, okay, Sthitadhi.
Yeah, okay. Thanks, Achilles, for the introduction, and also to Zlatko and Juan for sort of putting together this series of seminars and for asking me to give a talk here. Thanks to all of you for tuning in as well, and I hope that you are sort of safe and healthy amidst whichever wave your part of the world is seeing of the virus. Okay, so I'm going to talk about measurement phase transitions in all-to-all quantum circuits and quantum trees. I'll sort of motivate why is all-to-all sort of important here, and how do we go from there to quantum trees and so on. And I must mention that I'm trying to keep it sort of informal, so most of the details can be found in this preprint that we sort of put out in September, along with Adam Nahum, my colleague from Oxford, Brian Skinner from Ohio State, and Jonathan Ruman from Bar-Ilan. I'll be more than happy if you sort of interrupt me and ask questions, but I'm also happy to take questions at the very end. Okay, so with that, let me start on a somewhat sort of philosophical note that, as condensed matter theorists or statistical mechanics people, we often get extremely excited about phase transitions. And this talk is about a new kind of phase transitions in the dynamics of quantum entanglement. But sort of to take a step back, we normally think of phase transitions as appearing when you have two competing agents in your system, to state very naively. In that sense, measurement-induced entanglement phase transitions are no different, because what you will see is that they effectively have two competing agents. One is unitary dynamics of a generic quantum system, which normally tends to entangle systems. And competing against that, you have projective measurements, which try to disentangle the system. So to sort of put it pictorially, one of the ways in which over the last sort of few years we have come to think of generic quantum dynamics is via random unitary circuits. That basically, pictorially looks something like this. Although Juan probably doesn't like it, but I have space in the horizontal direction and time in the vertical direction, but that's how it's going to be in this talk. So what you have is a bunch of quantum degrees of freedom. It could be spins, it could be sort of spins with many more degrees of freedom, Q state spins and so on, but and so on. And then you have a bunch of unitary gates which try to make them talk to each other or make them interact. And eventually what you notice is that once this kind of a dynamics runs for a long enough time, then the entire system is entangled. The system goes to some sort of a maximally entangled state. There is long-range entanglement and so on. But then from this, you can sort of ask a question that what happens if this circuit is punctured by events which try to disentangle these local quantum degrees of freedom from the rest of the system. And one way in which you can have the sort of disentangling effects is via projective measurements. That here I'm sort of denoting by these red diamonds and these broken whirl lines. So for instance, a projection here, so imagine I have spin half systems in the circuit, and a projection here or a projective measurement here could be taking this particular spin and projecting it onto the up state and then normalizing the entire wave function. So what you immediately notice is, although it's not completely clear from this picture, but you can sort of imagine that you have a highly entangled quantum state, and then you choose one particular degree of freedom, say the leftmost spin here, and you measure it, by which you basically collapse it into one of its product states, if you want to, or not a product state, but one of its basis states, such that the entire state then becomes basically a product state between this particular spin that was just measured and the rest of the system. Now, the idea is that if the density of these measurements is high enough, then even at very late times, the state that you have, I mean, it's not a steady state in some sense, in any sense, but it's sort of a time evolving state. But at late times, the state never has a large amount of entanglement. For instance, in this picture, you can convince yourself that the leftmost and the rightmost spins were measured and no unitary or no interaction has acted on it. And hence, these are in some kind of in some kind of a classical state. And these two particular pairs have had just one unitary acting on them, but before that they were measured, and as a result, these two pairs are entangled with each other. These two spins are entangled with each other, but they're not entangled with the rest of the system. So this sort of suggests that quantitatively speaking, you can have two phases. When the rate of measurement or the density of measurements is low enough, you have an entangled phase where, which we'll sort of call a volume law entangled phase. And when I say volume, I am not automatically thinking of a spatial bipartition in the system. And I'm asking about the entanglement between the two parts. It could be characterized by something like a Renyi entropy or a von Neumann entropy. But the essential idea is that the entanglement follows a volume law. On the other hand, at large enough measurement rates, the system goes into what we call a disentangled phase, and we know that it has area law entanglement. That's basically saying that if I make a spatial bipartition somewhere here, the system or the degrees of freedom on one side of the bipartition can interact or are entangled with only order 1 degrees of freedom on the other side of the bipartition, and that's why you have an area law entanglement in the time evolving state. And this is kind of a picture that has been now propagated for a couple of years, and for all intents and purposes, we believe this picture to be true. There have been lots of works, a lot of them being numerical, some field theoretic works trying to establish that this picture holds. So what are the sort of open questions that we still are trying to understand in this field of measurement-induced entanglement phase transitions? So the first is the exact critical properties, because at the end of the day, this is a new kind of phase transition, and we would like to understand what are the universal properties of this new kind of quantum criticality. So we basically want the location of the critical point and, more important, the scaling near it. I mean, one can argue that the location of the critical point is not that important because it can vary from model to model. However, for practical purposes, you want to have it so that you can go and sit right at it and then study the scaling around it. Another question is, and this is something that I'll try to cultivate a bit more in the rest of the talk, which is this transition fundamentally of a quantum nature or of a classical nature? Let me not say anything more about this right now, because I'm going to say more about it later. Another open question is that, is this kind of a transition connected to other kinds of entanglement transitions, notably, say, the many-body localization transition, because we understand that is also an example of an entanglement phase transition, both in the sense of eigenstates of the Hamiltonian and the dynamics. There are other entanglement phase transitions, such as in random tensor networks, where the order parameter is the bond dimension and so on. So there is this whole sort of zoo of systems which show various kinds of entanglement transitions. And the idea would be that at least, is there a setting in which we can say something exactly about the universal properties of these transitions? Now, as we all understand, the fact that this is a local quantum circuit, the way I have drawn it, means that there is an underlying spatial structure. And this does complicate matters, as we all know from various other.
Someone's trying to ask a question, I think.
Yeah, sure, go ahead.
Is there any signature of this transition in some local quantity?
So this particular entanglement phase transition, no, because as you can see, I mean, I have kind of presented it in a way where I'm sort of saying that it's phase transition of the entanglement, which is not a local quantity by any means. However, if you think of many body localization as an entanglement transition, then of course there are local observables which do show the transition. Although whether their critical properties are the same as that of the entanglement transition is something that's not known as far as I know.
Thank you.
All right. So as I was saying, that the spatial structure does complicate matters. And one of the motivations for us was to understand if simplifying it, or even better, sort of completely getting rid of it, makes the problem exactly solvable or not. So that's going to be the focus of this talk. And I'm going to sort of talk about measurement transitions in all-to-all connected circuits. So what it means is that formally I am in infinite dimensions. I mean, some people might want to think of it as 0 dimension, but I'm calling it infinite dimensions because that's the way I understand it, in the sense that any two spins are neighbors in this setting. So one way in which I can draw the circuit is basically like this, where I have drawn word lines that go from any side to any other side. And of course, they're punctured by these measurements. Another way in which some of our collaborators found it easier to visualize was to arrange the degrees of freedom on a ring and have these gates, or these rectangular blocks which show the unitary gates, go between any two sides at random. And again, there are these measurements which puncture the circuit. So the rest of the talk, I would stick to this picture on the left. Now, of course, you might think that this actually does simplify matters, but it also brings in an additional complication, namely that in infinite dimensions or in these all-to-all circuits, the volume and area laws scale in the same way. So L to the power D and L to the power D minus 1 are not different anymore. So we can't really use the sort of spatial bipartitioning and entanglement between spatial partitions to understand the phase transition. And that basically means that we need to motivate new observables in order to understand this transition. So in order to do that, we
can I ask? So have people studied, the change in the statistics of the Schmidt values for these transitions?
Actually, that's basically what I am going to say. I mean, we are going to look at the operator entanglement of the non-unitary operator, which is related to the statistics of the Schmidt values. So yeah, you sort of caught it before I said it. Of course, you have to sort of be more careful because we don't have, at least in this setting, we don't have a fixed if time evolution operator, because the time evolution operator itself changes with time because of the randomness in the circuit. Okay, but as sort of Zratko probably already guessed, what we study is the so-called operator entanglement of the non-unitary operator V. So it's a non-unitary operator because there are these unitary gates, then you have these measurements in between. And the way I'm trying to sort of think about it is to say that think of this quantum circuit with measurements as a quantum information processor. And what we are asking is how much quantum information flows through the circuit in time. And that's quantified by the operator entanglement entropy of V, which is the non-unitary operator acting on state. And V, of course, is time dependent. So put it formally, the operator entanglement entropy is defined very much in a way you would define entanglement for any density matrix, except it's not the entanglement for density matrix, but for the operator, for the non-unitary operator itself. And you basically singular value decompose it into a basis for the initial time and a basis for the final time. And you have the singular values here. And then you come up with the nth Renyi operator entanglement entropy as given by this formula, which is sort of we understand well. Now, to convince you of the fact that this is actually a good observable to understand the transition, let me sort of very quickly argue that how it is qualitatively different in two so-called trivial limits. So the first limit is when there are no measurements, and this V is hence unitary. In that case, we know that the singular values of a unitary matrix are all 1 modulo a normalization, and any operator, any entropy is basically n log 2 at all times. The log 2 basically comes from the fact that I'm using spin half degrees of freedom. But what you notice is that it's maximal and is extensive in this limit where there are no measurements. But we can also take the other limit where the circuit is made up of only measurements and there are no unitaries. In that case, you notice that once you do the singular value decomposition, then there is only one singular value which corresponds, which contributes, in the sense that there is only one singular value which is 1 and all the others are 0. And that is basically that singular value corresponds to JT, which is the state or the product state to which the state has been projected to at time t, and J0 is the state down here to which the first set of measurements projects it to. So since we have only one singular value contributing in this case, the operator entanglement is trivially 0. And what this tells you is that this measure, the operator entanglement, does actually distinguish between the two phases, at least in these two extreme limits, and then it's a reasonable hope to say that this is going to be a good order parameter for the phase transition. So now we are often used to thinking about entanglement in the sense of a space-time picture, that there is a circuit and you, when I say space-time picture, I mean that you think of spatial bipartitions. However, this operator entanglement can also be thought of in a similar space-time picture. And the key idea is the idea of so-called minimal cut. The idea of the minimal cut is, in words, it's very simple. It's really the minimum number of links that you need to cut to break the circuit apart. Now, had we been interested in the entanglement entropy of a spatial bipartition, we would have anchored this minimal cut to the two spatial points which define the partition. However, what we are asking here is that what is the cost you have to pay to separate the final time of the circuit from the initial time? And we are basically asking, what is the minimum number of links you need to cut? Now, of course, one can say that when there are no measurements in the system, then you basically need to cut the world line of every spin, and that's why the operator entanglement is indeed extensive. However, when you have measurements, what you can try to do is you can try to find an optimal path such that the minimal cut actually goes through some of these measurements. And what that does is it helps you reduce the cost, because some of these world lines are already broken. So you don't need to pay that additional cost of breaking the world line. And hence, what you immediately notice is that introducing measurements actually reduces the cost of the minimal cut. I must add that this minimal cut is nothing but the so-called zeroth Renyi entropy, or some people want to call it the Hartley entropy, but it's all the same. Now, again, if you remember, I sort of motivated the limit where there were no unitaries in the circuit and only measurements, and I said that the operator entanglement is, in fact, 0. So, in fact, for the operator entanglement to be 0, one doesn't need to get rid of all the unitaries. You just need to have enough measurements so that you can find a minimal cut which goes through all measurements. In the sense that, for instance, in a particular example like this, you notice that, I mean, of course, I have drawn it this way, but in a given random realization of the circuit, it is possible to find a minimal cut such that it goes through all the world lines through a measurement point. And in that case, you don't actually pay any cost. But you also notice that if that is the case, the circuit is classically disconnected between the initial and final times. So this kind of a phase transition between a scenario like this to a scenario like this, and in the former, you have to pay some cost for the minimal cut. In the latter, you have to pay 0 cost for the minimal cut, is really a classical percolation phase transition that's determined by the geometric properties of the circuit. And this is a phase transition which we understand is completely classical. I'm going to present more results on this. But the question that we are really after is, does there exist a regime where the circuit is classically connected but quantum disentangled? Namely, that you are still above the percolation threshold in the sense that the circuit is, you can always find a path between the initial and the final times in the circuit, but quantum mechanically it's disentangled. And what we also find, and I'm sort of giving this away already, is that in this kind of a phase where the system is classically connected and quantum entangled, the properties of the unitary circuits survive for exponentially in system size long times. I must add that this is also related to the purification of an initially mixed state, because you can think that if you start with a mixed state and apply measurements all too frequently, then eventually you project it onto some pure state. Okay, so with this, we kind of conjecture a phase diagram, namely that there are two phase transitions. One is of a fundamentally quantum nature, the other is of a fundamentally classical nature. At the classical phase transition, the zeroth Renyi entropy or the Hartley entropy goes to zero. This is just a classical percolation phase transition. And in the quantum phase transition, it's really the operator entanglement that goes to zero. And the rest of the talk will basically be dedicated to trying to understand these two phase transitions. So in this work, we basically took 4 approaches. One was to first solve the classical problem, because that obviously gives a bound to the quantum transition. Then I'm going to motivate that the entanglement transitions can actually be understood by mapping it onto some kind of an entanglement transition on quantum trees. This is going to form the majority of my talk. And the final thing that another thing that we did was simulations of quantum circuits. It was just to actually take this finite size circuits and simulate them and see what we get. In the paper, we also came up with some conjectural field theories for these phase transitions. But in this talk, I'm mostly going to focus on the entanglement transition on quantum trees and quantum circuits and the simulations of quantum circuits. I'm not going to say anything about the field theories. And I'm also going to briefly motivate the classical minimal cut problem. I think at this stage, it's a good time for me to stop and take questions if there are any.
So if you can't find a classical minimal cut, what is the probability?
What do you mean can't find?
Suppose I am on the side where I can. Suppose I'm on the extreme right of your previous page. What are the implications for the Schmidt values of?
Oh, in that case, you know that the operator entanglement has gone to zero. So
okay, so you're saying this is an obvious statement that the operator entanglement is.
Because what you have done is you have classically disconnected the
yeah.
So yeah, you have.
Yeah. Okay, I see. I think I see. Thank you.
I was maybe jumping ahead a little bit, but normally we associate phase transitions with some sort of non-analytic behavior, and the sketches, and I appreciate they were only sketches in your previous slide, everything looked smooth.
Well, this is not smooth, right? Because this function is finite here and zero everywhere else. This is not
right, but it could still have maybe some essential singularity, and it's continuous, and all its derivatives are continuous.
We don't have that, so I'll actually present the exact scaling forms.
Okay, thank you.
Yeah, and this is really just a sketch. I mean, we have data. Okay, so let me start with clarifying the model and the definitions that I'm going to use in the rest of the talk. So again, a node-to-all circuit with these measurements pictorially looks like this, where these blocks are 4x4 Haar random unitaries, and they appear with a rate proportional to 1 minus R. And then these diamonds which break the world lines are projective measurements or projections which appear with a rate proportional to R. So there are 2 protocols that we sort of use. One we call the true measurements, where whether we project the spin up or down really depends on the Born rule probability. And this leads to some non-trivial correlated outcome probabilities. The other protocol that we used is the protocol of so-called forced measurements, where we actually don't care about the state of the system or state of the spin that's going to get measured, no matter what we project it up. So this is roughly like post-selection, where basically we throw away all the runs where any of the spins that got measured was. Okay. So, but of course, these two protocols are identical as far as the classical problem is concerned, because in either case, all it does is it breaks the word line. So let me quickly go through the classical problem. So in order to do that, the first thing you notice is that this all-to-all circuit has an equivalent representation in the form of a graph, which is constructed as follows. So we take these unitaries and think of these unitaries as the nodes of my graph. So here what I have done is I've drawn it in a way where these unitaries are color-coded with the colors of the graphs. And then the world lines of the spins would have formed the edges of this graph. However, you can see that not all the edges are present, and that's because many of these edges were broken because of the presence of measurements. For instance, you see that this edge or this word line between the blue and the green unitary is broken by this particular measurement. And as a result, there is no direct link between the blue and the green nodes here. And sort of this is how you get this particular graph. And then what you do is you take a particular node as your so-called seed node and try to arrange all the other nodes according to their distance from the seed node. And what you find is that generically these graphs locally look tree-like. And that's not a big surprise, because what you have at the end of the day is a graph with a large number of nodes, but finite connectivity. So a random graph like that is always locally tree-like. Of course, there are loops, but they are of the size, or their size is typically of the order of log n being the number of degrees of freedom I have in my system. Okay, so once it's a tree, then it's useful to also define a quantity p, which is a probability that a site is measured before any unitary acts on it. So namely, let me take a particular site and I ask that if I go up, then what is the probability that it's measured before a unitary acts on it? And that's very simply related by the rate of measurement as something like this. The reason it comes about like this is because R is the probability that a measurement appears, or is the rate that the measurement appears. And in the denominator, you have the rate of the measurement and the rate that a unitary appears, but there's a factor of 2 here because the unitaries are 2 local, so there's twice the probability that it gets chosen for a unitary to act. So then it sort of is quite a trivial exercise to understand the percolation, to solve the percolation problem on this particular tree. We all know that a classical percolation transition on a tree with connectivity 3, basically for the tree to survive forever, you need 3 times p minus 1 to be greater than 1. And that basically gives you a critical p of 2/3, which means that the critical rate of measurements is 4/5. So that's sort of simple analytic calculation that you can do, and that tells you what the classical percolation transition is. You can also sort of understand that on a tree-like graph, the percolation probability between the initial and final times decays exponentially with time. Now, what do I mean by time here? Because this is a classical percolation problem. So time really is, if you go back to the construction of this circuit, then the longer you let the circuit run in time, the more and more number of possible generations you have in your graph or in your tree. So what I mean by time here is that the percolation probability between the root site and the leaves of this tree, that decays exponentially with the size of the tree. And so we can actually solve this classical problem numerically. And let me say that this result is not from a tree. This is actually from simulating the classical circuit, or simulating the circuit with measurements, but classically. So what we do find is that the exponential decay timescale has a very nice scaling form, which goes as n to the power 1/5 times the scaling function of n to the power 2/5 times delta r. Delta r is the distance from the critical point.
Question.
Sure.
On something maybe you explained it before. So that circuit becomes a tree. Is that statement exact? A tree has no loops.
No, this statement is not exact. It's true only locally.
Okay, so there are, as usual, there are probably loops which go as log the length or something like that.
Log n, yeah, log of the system size. Yeah. So what we do here is, I mean, that's why we sort of simulate this. These numerical results are from the simulation of the circuit, which actually has the loops that you're talking about. But we find that the critical behavior is really the same as that of a tree. And I think this is the usual argument that close to the transition, it doesn't really matter whether the loops are long, because your entanglement becomes very, very small by the time you get to the scales of the loop. So this is the kind of argument that people also use in the context of localization when you're talking about equivalence of localization problems on trees versus, say, random regular graphs. Okay, so given that the exponential decay timescale of the percolation probability has this kind of a scaling, form, you can conjecture that the minimal cut has a similar scaling form. But then, as I said, that you make an assumption that there is a very large time window over which S0 is extensive but independent of time, because what I was claiming was that the properties of the unitary circuit actually survive for exponentially long times. And that's also something that you can see from numerical calculations. It tells you that the minimal cut should have a scaling form, which basically goes as the distance from the critical point to the power 5 half. Of course, this is an argument based on the scaling of this exponential decay time scale, but of course you can actually compute the minimal cut numerically. And we do find that it looks like as you get closer to the critical point, the scaling form or the scaling of the minimal cut is the distance from the critical point to the power 5 halves. Now, you can also analytically argue for these scaling forms by mapping this problem to a percolation problem on layered Erdős-Renyi graphs. And each layer of the Erdős-Renyi graph is really each time slice. So think of the Erdős-Renyi graph as just being a collection of points which have random links between them depending on the average connectivity. But what you can do is you can say that I'm going to put random points on each layer, and then I'm going to connect these layers so that the average connectivity of each point is the same. And this is something that has really been studied to death in the literature. And you can do field theoretic calculation, or you can do a calculation in the continuum limit, whichever way you want to call it. And you indeed recover the same critical exponents. So that sort of gives us enough confidence that the classical phase transition indeed is similar to that of a tree, because we have the results from the trees, we have the numerical results from our circuits, and we have the analytic results from the mapping to these Erdős-Renyi graphs. Okay, so the phase diagram so far now then is that you have one phase where the circuit or the graph is classically connected and quantum entangled, and you have another phase where it's classically disconnected and hence obviously quantum disentangled. The critical rate of measurement for this is 0.8, and the scaling of the Hartley entropy or the zero Renyi entropy is, there's a power law scaling near this critical point. And what we are after is trying to understand this intermediate phase. I should not call it an intermediate phase, but intermediate regime, which basically sits between the quantum critical point, if present, and the classical critical point. And for that, I'm going to study entanglement phase transitions in quantum trees. But I guess I'll take a pause here to see if there are any questions, at least on the classical. Okay.
Hi, Sthitadhi, this is Srijit.
Hi, Srijit.
So this is a question about slide probably in the previous section, but so in the you mentioned two possible kinds of measurement. One is full projection, and the other is a true measurement. So in the case of true measurement, is it easy to see that this also leads to the singular value decomposition having only one term?
If you are, okay, so no matter whether you have true measurements or forced measurements, you are doing a projection and you are disentangling the site that the measurement happened on. So classically speaking, you definitely cut the circuit. So if you sort of classically look at the circuit with a link missing, you don't know whether it happened because there was a true measurement or a forced measurement. So if you are beyond the classical critical point, then yes, it doesn't matter whether you have true measurements or forced measurements because they have the same effect, namely of, they have the same classical effect, namely of cutting the circuit.
Okay, thanks.
But of course, as probably you already guessed, the critical property of the properties of the quantum phase transition and the properties of the classically connected but quantum disentangled phase can be different depending on whether you have true or forced measurements. And because in the case of true measurements, the outcomes are actually correlated.
Okay.
Okay. So let me go on to entanglement transitions in quantum trees. And as I was kind of trying to motivate in the previous section, the graph really is a tree. But then handle it quantum mechanically, you very quickly realize that this tree can be, or the quantum information that flows between this tree can be understood as the quantum entanglement between the spin at the top of this tree and the set of spins at the bottom of this tree. And that really is the quantum information flowing between the base and the apex of the tree. So we play sort of the same game. We try to quantify the entanglement entropy between the apex and the base of the tree. And sort of the usual game is you again do a singular value decomposition and write the tree something like this. Now, what you notice is I only have two singular values here. And that's simply because at the top of this tree, I have a single spin half, and that has a local Hilbert space dimension of 2. But at the same time, what I would like to do is I would like to work with normalized singular values, which basically means that the entire entanglement properties of the tree is controlled by only one number, and I choose that to be the minimum singular value squared, and I call it Z of k for a tree with k generations. And once I have Z of k, then I can again very simply compute the Renyi entropy between the apex and the base by this formula. I mean, the formula is not important, but the take-away message is there is only one number for a tree with k generations I need to worry about. But it's also useful to understand a bit the structure of these node tensors, because these essentially are, at the end of the day, quantum mechanical operators. So a node tensor here basically looks something like this. So remember that this is the same unitary gate acting on two spins that I had in the circuit. But what I have done is I have taken one of the indices of this tree and folded it down so that at the top I have only 1 and at the bottom I have 3. And between or on any one leg of this or on the top leg of this unitary operator, I actually put an operator Q, which is nothing but the measurement operator. So it can be a measurement operator or a projection operator with probability P, or it could be identity, namely there is nothing here with probability 1 minus P. And this is the usual random unitary. Now, you might notice here that I have already put in a projection onto the upspin. So implicitly, I have already gone to the case of forced measurements. And the reason behind that is if I have forced measurements and these hard random unitaries, then this entire tensor is statistically invariant under any U2 rotation of the indices. Namely, notice that each of these indices can take 2 values because they correspond to spin down, and I can do a U2 rotation on any of these indices, But if I have forced measurements, then it's all invariant statistically. So the massive simplification that happens because of this is that we need to keep track only of singular values, and we don't need to worry about the singular vectors of this node tensor. Had it been the case of true measurements, I would have actually needed to keep track of the singular vectors as well. Now, the massive simplification that happens because of the requirement to keep track only of singular values is I can solve this problem recursively. So a tree with k plus 1
I ask a question before you continue. So you define a node tensor as something with one edge coming in and a bunch coming out. Is that correct?
And 3 coming out, yes.
3 in this case, yes. But I mean, you basically go and select at random one, and okay, that's what you said. That for this choice of parameters, it doesn't matter which one. But okay, yeah. So but all you're saying is that the node tensor is something with one thing coming in, 3 prongs coming out, and that's it.
Yes. And that's sort of stipulated by this tree structure of the graph.
Right, I see. Thank you.
Okay, so as I was saying, that you can take 3 trees with k generations. That's your blue, orange, and green trees. You stick them onto the 3 downward indices of the 4x4 random unit tree, and you sort of on the remaining fourth leg, you with probability p, you put in a measurement. And that basically gives you a tree with k plus 1 generations. For people who want to sort of see it mathematically written, you basically write it again as a singular value decomposition of the tree with k generations, and put in this particular unit tree. Now, as I said, that because I need to worry only about the singular values in this case, but and remember that a given tree is fully characterized, or the entanglement properties of a given tree is fully characterized by one number, which I was calling zk. So what it means is that the z for a tree with k plus 1 generations can be written as a nonlinear recursion relation of the 3 incoming singular values, which I call zk, zk prime, and zk double prime. But this happens with a probability 1 minus p, because with probability p, this particular node gets, or this particular measurement is, or there is a, with probability p, there is a measurement here, which makes zk plus 1 0. So this is the central equation that we then kind of need to analyze. And what we do is we say that near the phase transition, these numbers are all very small. So we can also study a linearized recursion relation, where basically we keep terms up to leading order, and then you effectively have a linear recursion relation. The crucial point is that no matter whether you want to study the nonlinear recursion relation or you want to study the linear recursion relation, this function f or these coefficients ai's depend explicitly on the matrix elements of U in a way that it's analytically tractable, because at the end of the day, U is just a 4x4 matrix. So it has a finite number of matrix elements, and you can write it explicitly and try to take averages over the Haar ensemble for U. But another advantage of this is that you can use the so-called tool method to actually very, very efficiently simulate this recursion relation numerically. So the idea is very simple. You basically take a whole bunch of starting zk values that generates the distribution of zk. And then what you do is you randomly select 3 of them from the pool and use them as inputs to your recursion relation, or inputs to this recursion relation, and that generates one member of your pool for the next generation. So in this way, this is really sort of making it into a recursion relation for the entire distribution of zk's. So let's say that we do this calculation either numerically or analytically, and ask the question that what do we get? So first, let's start with the linear recursion relation. So let's say that I am in a phase where the measurement rate is below the critical measurement rate. In that case, what we find is that this initial distribution, let's say that I started with a narrow distribution of zk's, it increasing k very rapidly moves to, or not actually very rapidly, it moves linearly in k to the right. But notice that this is a distribution of log z. What that means is zk, or the distribution of log zk, is growing linearly in k, which means that zk on an typically is growing exponentially in k. However, you might say that, well, zk has to be bounded from above, so why is it allowed to go off to infinity? Because zk is a normalized singular value. That's just because I'm simulating a linear recursion relation here. But then you can go to the other phase where what happens is exactly the opposite. Zk typically decays exponentially with the generation number, and the distribution actually moves linearly to the left with some velocity. And the phase transition really happens at the value of p, where this velocity is 0. Now, then you can ask the question that, okay, what happens if I now introduce the nonlinearity in the recursion relation? In that case, the so-called disentangling phase, which was for a measurement probability greater than the critical value, nothing really changes. The distribution actually still moves to the left and goes off to infinity, minus infinity, as k goes to infinity. However, in the entangling phase, what the nonlinearity does is it sort of pushes this distribution up against a wall, which is basically the wall corresponding to the maximum value that log of zk can take. Now remember that the maximum value that zk can take is a half. So it sort of gets pushed up against a wall at log of. And that basically means that, in fact, you can also see numerically that as k goes to infinity, this distribution becomes stable and doesn't change anymore with k. So what that means is that k goes to infinity, z of k goes to some order 1 value, and that is sort of the signature of an entangling phase. To put it more kind of quantitatively, as I said, that from the linear recursion relation, what you find is that the log of the typical value of zk grows or decays linearly with k. And that's what you see here in this plot. That if my measurement rate is, or measurement probability is quite low, it grows with a positive velocity. If it's quite high, it decays with a, or goes down linearly with a negative velocity. In between, there is a phase transition where the velocity is actually 0. So of course here, numerically, we cannot find the exact location of the transition. There are analytic calculations that we can do. I'm going to flash them in the next slide. But more importantly, notice that when the nonlinearity is introduced in the recursion relation, the so-called disentangling phase at high values of p stays the same. The z typical still decays exponentially with k. However, remember that the distribution was getting pushed up against a wall in the entangling phase, and that's manifested in the fact that the typical value of z actually plateaus out to its order 1 value, which tells you the finite entanglement that you have in the phase, in the entangling phase. Okay, so now that we sort of know what's going on, we can actually go and analyze the recursion relations in much more detail, and without sort of bothering you with the details. What you can basically do is you can map it onto a traveling wave equation, as was done by Derrida and Spohn in 1988. Think of this distribution that was moving as some kind of a traveling wave in fictitious time k, and then you find out what the kind of velocity of this wave is, and you can come up with some expression for this. Now remember, what I had said was that these recursion relations actually depended in some way, which was analytically tractable on the matrix elements of the unitary operated U. Now, remarkably, for the Haar ensemble, you can actually do these averages exactly, and that gives you a critical point. And don't ask me why it's written like this. The funny thing is that we actually did it on Mathematica, and Mathematica gave us the answer in this. So we decided to keep it. Now, the crucial point is that this value, if you sort of numerically evaluate it, it gives you 0.749. Now, this is actually very close to the classical critical point, nevertheless is different. Of course, you can also ask questions about the scaling, and you can analyze the behavior of the recursion relations around the critical point. And what you find is very interesting, namely that the scaling is extremely rapid. Namely, Z typical has an exponential scaling with the distance from the critical point. Basically goes as e to the power minus some constant over the square root of the distance from the critical point. And this is actually distinct from the kind of power law scaling that we had for the classical problem. So, and this is a numerical check, whether this is a numerical check of these analytic calculations. And what you find is that with the hard, I mean, this is another ensemble we had tried, but I'm not going to talk about this. But what you see is that notice that there are two logs here. So that's why it becomes a power law, and the power is well approximated by a minus half. So with that, the phase diagram is now more or less complete. We have now located the exact quantum critical point, which is distinct from the classical critical point. And we know that the form of the scaling near this quantum critical point is also qualitatively different from the classical critical point. So that in a way sort of finishes the analysis on the basis of entanglement transitions on trees. And I'm going to stop here for a while to take any questions, but in the remaining 5 minutes or so that I have, I'll flash some results on the simulations of the quantum circuits. But I think I can take questions on the trees if there are any. Okay, so if there are not, then let me quickly flash some results on the operator entanglement entropy, but now computed exactly for the circuits. Of course, these results are numerical with tiny system sizes, so they are nowhere near as clean or as nice as the results I presented previously. But nevertheless, what we find is that in the so-called entangling phase, with increasing system size, the operator entanglement density seems to grow. Of course, with these limited system sizes that we have, still went ahead and we got into the wind and said that, okay, let's do an extrapolation to infinity. And what you seem to find is that there does exist a plateau in the operator entanglement entropy in the entangling phase. And we think that this plateau is basically reminiscent of the fact that the the properties of the unitary phase, namely a finite operator entanglement entropy, survives for exponentially long times in the entangling phase. If I go to large values of R, then of course the entanglement drops to 0 in order 1 time. And if you sort of look closely, it suggests that it drops quicker for a larger system size. Now, the problem with this analysis is that this is an operator entanglement entropy. So you really have to sort of evolve a gigantic matrix in time and then keep on doing a diagonalization or singular value decomposition to get these. So it's kind of limited to very small system sizes. Ideally, what you want is something which is based on evolution of quantum states, because then you can do slightly larger system sizes. So we come up with this observable, which we call the state overlap. So the idea is quite simple. We start off with a particular state, which is a product state, so zero entanglement. In this case, we start with a state where all the spins are polarized in the x direction, positive x direction. And we apply this unitary circuit, this non-unitary circuit on the state. We eventually get another state, which we call psi1, which might or might not be entangled, and which is basically given by the operator acting on the state, and then there's a normalization. Then we prepare another initial state, which is also unentangled, but orthogonal to this particular state. That is, we prepare a state which has all the spins polarized, but in the negative z direction. And we apply the same non-unitary circuit. And we call this psi2. And then we say that the quantity of interest for us is the overlap between these two time evolving states. And or 1 minus that is rather the distance between these two time evolving states. Now again, had the circuit been unitary, then the distance between these two states would have stayed the same, and you would have had zero overlap at all times. Had the circuit been only measurements, then you basically would have in order one time, or in order one time, you would have basically measured all the spins and gone to a state which is a product state, which is the same for both of them, and you would have gotten an overlap of one in order one time. However, so that's why we think that this is a good kind of diagnostic for the entanglement transition. So now you simulate this, and what we find is indeed the overlap, or the distance between the two states, actually decays with time exponentially, both in the entangling and the disentangling phase. However, there is a crucial difference. In the entangling phase, the associated time scale of this exponential decay seems to grow with system size. You can see that the curves become sort of shallower and shallower as we increase system size. Whereas in the disentangling phase, the time scale of the exponential decay saturates with system size. So this is again a reflection of what I have now sort of repeated many, many times, namely in the entangling phase, there is a time scale which is exponentially long in system size, over which the system retains properties of the unitary circuit. Whereas in the disentangling phase, this time scale really is order one, and the system very quickly realizes that it's being measured over and over again. So now notice that this A of R, which is the coefficient of the system size in this exponential time scale, we say that it's going to be finite, as it seems from the data, it should be finite in the disentangling phase, whereas it should go to 0 in the disentangling phase, so that the time scale is independent of the system size. So we compute this A of R, and we try to plot it as a function of R, and we get something which looks like this. Now, this is of course not very nice, because at the end of the day, these system sizes are say 20. The results that I showed with trees, we went up to say 300, 400, or 500 generations, which means that we effectively simulated a system of 3 to the power 500 spins, which is probably the thermodynamic limit. But nevertheless, we sort of put this data of A of R versus R, and we also kind of put this curve, or that we predict from the tree. And of course, this is not a confirmation of anything, but at least it's not completely inconsistent. But let me point out one sort of major difficulty in the numerics of this problem, namely that this kind of a scaling form means that this quantity A of R is actually absolutely tiny way before the transition. The transition, remember, the quantum transition from the tree, remember, is at 0.75. But this A of R becomes absolutely tiny, even say when you cross 0.6. And the system sizes that we have are nowhere near large enough to realize that. But at least these quantum numerics are not inconsistent with what we predict from the tree. Okay, so with that, I think I'm sort of out of time. And let me go to my summary slide. So I sort of motivated why we study measurement-induced entanglement transitions in all-to-all circuits. The hope was to go to all-to-all circuits and remove complications coming from spatial structure to sort of have some analytical insights into the problem. And then we sort of stumbled upon this fact that these kinds of circuit geometries are very close to or the phase transitions are very similar to entanglement transitions on quantum trees, which does allow certain analytical results to be obtained. And we have, and eventually we came up with the following phase diagram. So of course, at very large values of the measurement rate, the circuit is classically disconnected, obviously quantum disentangled. That is separated from the other phases by a classical percolation transition that has a power law scaling, or the zero Earth-Renyi entropy, or this minimal cut has a power law scaling near the phase transition. Then there is an intermediate phase or regime where the circuit is classically connected but quantum disentangled. And that basically is, or this quantum phase transition is separate from the classical phase transition. And in fact, by studying the entanglement properties of the tree, we could actually compute the quantum critical point exactly along with the scaling form near this quantum phase transition, or the scaling form of the operator entanglement. And that basically is very distinct from the classical phase transition critical properties. So the upshot of this work is that the measurement-induced entanglement phase transitions are actually distinct from the classical transitions, and in this particular setting, at least, you can have some exact results. With that, let me thank you for your attention.
All right, thank you, Sthitadhi. So are there any questions?
Yes, I have one.
Yeah.
Nice talk. About the last part of your talk, I want to understand a little bit the statement that in the disentangling case, you still kind of evade the orthogonality catastrophe for large system size. That's a bit puzzling.
No, so
Can you explain?
Yeah, so the idea is that, of course, in the disentangling phase, if you take a finite system and run time to infinity, of course, basically you will make the overlap go to 1, because if you have a finite system, then with some exponential probability, you would basically measure all the exponentially small in system size probability, you will measure everything before you apply any unitary, and then you will collapse the overlap to 1. But notice that this probability is exponentially small in system size, which means that you have to wait for an exponentially large in system size time to wait for this to happen, which basically gives you this exponentially large time scale in the disentangling phase.
So you're saying
that's
that
actually a good point. Yeah.
So in the right-hand side, you say that this will happen again for long times.
No, in the right-hand side, this will happen at order 1 times, or at some times which is independent of system size, because you have measured so frequently that, or the rate of measurement is high enough that the time scale over which the two states become identical to each other just stops depending on system size.
Thank you.
Can I ask one then? Unless. So I have a couple. So one is these recursion relations, you obtain them by using the symmetry that's only there for forced measurements. Is that correct?
Yeah, that's right.
So if I don't have forced measurements, I mean, is there any avenue to get some results, or have you looked at any results apart from numerics? And I mean, how do things like this critical R and so on change?
Okay,
if I don't have forced measurements.
So if you have true measurements, then okay, so of course what you can do is you can still, I mean, okay, the idea of the tree stays intact, but you cannot use this pool method to do the numerics. You would actually have to keep sort of decomposing the tree over and over again, so that you take the singular vector or the eigenvectors into account as well. So that's the numerical calculation for the tree that you would want to do. And that probably is going to restrict you to not more than probably 10 or 20 generations, which is still not bad, because you're effectively simulating 2 to the power 10 or 2 to the power 20, 3 to the power 10 or 3 to the power 20 generations. So we did look at it, and there are a few things that we can say, which is we don't think the disentangling phase with forced measurements is going to look any different, in the sense that if you have forced measurements or if you have true measurements, but between any two of these measurement events, if you have enough number of unitary operators, then your system or your state is completely scrambled. So it doesn't really matter whether you measure up or whether you project up or whether you project down. Now, then comes the point of, can we actually make a statement about whether the critical point shifts to the right or shifts to the left? So again, we think that the critical point probably does not shift. And the simple reason is the following. Namely, and this is a very hand-wavy heuristic argument, but you notice that near the phase transition, the entanglement is very small. What that means is between any two measurement events, the system did not get scrambled enough. So if at some point you measured up, then it's highly likely that you will keep measuring it up over and over again, which is the same as saying that you did a forced measurement. The only caveat in this argument is, again, that whether there is some correlation in these eigenvectors which kind of propagates and destroys the argument that I made. Yes, that can happen. But again, the fact, okay, and part of it is I'm sort of relying on the fact that near the phase transition, near the quantum phase transition, you have this kind of, let me go to this plot. You have this, okay, so if you think of this as some indicator for the amount of entanglement in the system, it really is absolutely small near the transition. But yeah, that's the best I can make, best statement I can make. I mean, what we did see is that for low values of R, forced and true measurements didn't make any difference, but that's kind of obvious because so many unitaries act between measurement events that it doesn't really matter whether you project up or project down.
Sthitadhi, in the correspondence between the results on the tree and on the actual lattice or actual system, so the singular values that you're getting in the tree calculations, is this analogous to the singular values of the operator V? Because you have folded some of the lines that should be in the backward direction into the forward direction.
Yes. Okay. So generally no, but again, let me sort of try to give you this cartoon picture. So of course, the entire circuit you can think of being constructed of many trees which are sparsely connected to each other. So imagine the simplest case where I take two trees and I connect the sort of the apexes of the two together. So there's a tree which goes down like this and there's a tree which goes up like this. And I'm sort of using this as a caricature for what goes on inside the circuit, at least near criticality, because near criticality, the circuit anyway is actually quite sparse. And then what you can say is that in order to cut the circuit into half, you need to cut it, and you don't need to actually worry about cutting links in the middle of the tree. All you need to worry about is trying to cut the link that connected the two trees. And then you have sort of separated the circuit into two parts. So in that case, what happens is that you can say that if the circuit was large enough, then the singular values of the two trees that you actually connected together as something like is basically ZK. And by cutting that bond, the error that you introduce in the singular value of the entire circuit is proportional to ZK again. So now what you can sort of say is that on an average, you need to cut order n such links to completely separate the circuit, because at the end of the day, the transition happens at a finite measurement rate. I mean, it's a measurement rate, so you need to, and that basically tells you that in a way, the singular values that you get from the trees are a bound or an upper bound to the singular values that you can get from the circuit. But there's another argument to say that the singular value from the tree is like a lower bound to the circuit. And that is to say that if you now start connecting various trees, you effectively reduce the connectivity, right? Because if the so I mean, you sort of run with that argument, and I mean, both of these are heuristic arguments, but one gives you an upper bound. One gives the singular values of the tree as an upper bound for the singular values of the circuit. The other gives you it as a lower bound. So we think that probably the singular values of the tree is more or less exact or more or less correct for the singular values of the circuit in the n going to infinity limit. But the upper bound argument is slightly more rigorous, if I want to call it. And that's just because you imagine the circuit to be made up of trees joined together, partly connected, of course.
Thanks.
So maybe another very general question. So this is for all connected. Okay, the measurements are local, but the unitaries are, you know. So what if I force the unitaries to act only on nearest neighbors, or if I put anything on a line or into the grid or so. I mean, if I had some degree of locality, that's, I guess, the question. What in this entire story would change, or do you have any idea?
Well, we think that these critical exponents are not going to are going to change. The critical properties are definitely going to be different, but there is a big fight going on about it, about the nature of the critical point in local circuits with measurements. So as far as I know, there are no exact results. I mean, people have done numerics and found different kinds of scaling collapses. So what is sort of worrying is that, or what makes you sort of worry about those numerical results is even in this all-to-all type models, first, you don't actually get mean field scaling per se. And second, you notice that you need to go to such gigantic sizes to actually see numerically see the results that you get from analytics. So who knows what's going on with these, with the numerical results of the circuits with local. I mean, there are some results which try to map it onto other kinds of conformal field theories and come up with some results, but yes, there are approximations involved there. But yes, I mean, the existence of the transition is probably not disputed.
Okay, yeah, thank you.
Andreas has the raised hand.
Yes.
Yeah.
Can you comment on why it seems that this 1/n scaling seems to fail at large times?
Sorry, can you say that again?
Yeah, in this picture you have here, this 1/n scaling that you show here for large times, it seems to become worse. So there are deviations from this 1/n behavior.
Yes,
the collapse
sure.
that you show.
Yeah, here, for instance.
Yeah.
Yeah. Okay, okay. The thing is, at the end of the day, you have to realize that this is only from 6 to 12. So we ourselves are not, we are not going to bet our lives on anything quantitative from this plot. I mean, what we just wanted to say was that it looks like in this large system size, large time limit, there is a plateau in the entanglement density. But I mean, as I was saying, that these system sizes are absolutely, but we just wanted to do this as a way of sanity checking things, not to come up. I mean, for instance, even when I go to say 20, which is still not large, you can barely see a transition. I mean, if I had not put this curve, or if I did not have the results from the trees, probably one would have believed that either there is no phase transition or there is a phase transition at 0.6. Whole thing is a finite size effect. So, I mean, these were just to sort of make sure that what we are doing with the trees is not a complete imagination. I can probably make a comment that there are some works on Clifford circuits where they do larger sizes of the order of a few hundred spins. There they also find transitions and some associated critical behavior. I'm not very familiar with those.
But you did say that, I mean, that if you have local, for example, circuits, then you do expect completely different critical behavior.
Yeah, definitely, yeah. I mean, that was the kind of reason for trying to do these field theories, because we wanted to see if we can get some kind of an upper critical dimension and make a statement about finite but large dimensions. But that is kind of, I mean, if you come up with an upper critical dimension of 10, that's not particularly useful. You would rather think of it as an all-to-all circuit.
All right, are there any other questions, or should we call it a day? Or we can switch off the recording in case anybody's too shy to ask these things in public. So